so somehow answering popular demand, I decided to include here yet another, probably more interesting example of algebraic solution of the Schrödinger equation, of the eigenvalue problem, and actually a very important example, because we all know quantization, we all know the energy levels and their degeneracy for the hydrogen atom, but in standard textbooks, this is usually derived by solving differential equations, Schrödinger equation, but in this differential form. To set the stage for this, let me start from a classical mechanics problem, Kepler problem, for which, of course, we know that the Hamiltonian is the sum of the kinetic energy and the potential energy for the attractive Coulomb potential. And it's not essential, but let me remind you that K is E squared divided by 4 pi epsilon 0 if we want to work with the legal SI units. Now, already a long time ago, I don't know exactly when, but certainly in the 19th century, two physicists, Runge and Lenz, I think first in Germany and the other in Russia, noticed that there is interesting vector which has some special relation to the Coulomb or Kepler problem. Well, of course we see it's a vector, but it's a very special vector. It turns out that it's a constant of motion. It's not difficult to check that indeed this is the case. Let's differentiate A with respect to time. It's 1 over m, of course. And now L we know is a constant of motion for any central force. So out of these two guys, we have to differentiate only the first one, namely momentum, because the other term is 0, right? Now this is minus k, and if I differentiate this guy, that will give me velocity divided by r. I hope this is distinguishable. But also, I have to differentiate the denominator, and that is 1 minus 1 over r squared. So this is plus k r over r squared times r dot. Okay? Now, this fellow, of course, satisfies the Newton equation. So for the problem at hand, this is minus k divided by r squared, r over r. That's a central force which has 1 over r squared dependence, yes? So I can plug in this fellow here. Yes? Because so my A dot is equal cross, and L we know it is what is this thing? R dot times R divided maybe by one more R. R times R dot divided by R is nothing else but the scalar product of velocity with R over R, right? It's the same. It's a radial component of the velocity. Okay? So now, the next step is very simple. We know that we can expand this double vector product, and it will be, one term will be proportional to R, and one term will be proportional to V, and by applying this formula, you can immediately, very quickly check that this fellow cancels against this, and this fellow cancels against this. Yes. So indeed, Runge length vector is a constant of motion for the Kepler problem. Okay. Now, do we know what is its graphical representation, so to say? How is it related to the Coulomb or Kepler problem geometrically? Well, first one can check something disappointing, namely, if we take the circular orbit, here is the center of motion, here is the circular orbit, then we know, of course, that radial velocity in this case is 0. We know that this transverse velocity is nothing but R times phi dot, where phi is the angle here. And these two observations are sufficient to check, to verify that in this case, the whole Runge length vector is just 0. So it's not interesting at all. But had we taken an elliptic orbit, it would be a very different situation. It is still, just look at the formula that I have erased, and you have this formula probably in the notes. It is A is lying in the, it's non-zero first, but second, it's lying in the plane defining the orbit. And one can easily check that actually it defines the axis. So it's a constant of motion which is telling you about the position of the ellipse in the plane perpendicular to the angular momentum. Thus, it is of course orthogonal to L, which is quite nice. Now, it is also, I think, for most of you, there are not too many right now, more or less clear that this presence of this Runge length vector is a specific feature of the Coulomb interaction. If we had other power of R in the denominator, some other attractive force, then as you probably remember from classical mechanics, the resulting trajectory could be circle, that's fine, but if it is squeezed a little bit in one direction, then it forms a rosette. It goes around with this, what people call perihelion motion. Yes, actually, you know that has some meaning for the relativistic corrections to the Kepler problem. And the perihelion motion rotation is actually measured, and it is measuring a deviation from exact Coulomb or Kepler interaction. Yeah. By the way, its measurement and the fact that it can be also So, there is something special about 1 over r potential, namely that there are closed orbits. Yeah? And this speciality is somehow hidden in the properties of the Runge-Lenz vector. So much about classical mechanics that maybe you heard about or you did not hear about. Now, let's go to quantum physics. So, first, is it easy to define corresponding quantum operator, corresponding operator in quantum mechanics, which has a lot of properties of Runge-Lenz vector? Yes, but one has to pay attention. If I have this vector product of momentum and angular momentum, and if I take Hermitian conjugate of this fellow, just as I was pointing out several times, for the product it reverses the order. So this fellow is equal to L cross P, and this is of course equal to minus P times RL. In other words, P cross L, even though P and L are nice, decent Hermitian operators, is anti-Hermitian. Okay, so we cannot just copy the same formula and say, okay, that would be nice operator in the for the Schrödinger equation for the quantum mechanics. Instead, we have to be slightly more cautious. We have to write 1 over 2m, and now P cross L, yes, P cross L, minus L cross P. Now this combination is of course Hermitian as we want. The remaining term is fine. So it is like this. Okay, so now we have defined a corresponding Hermitian operator, which is a decent quantum mechanical object. And we can start looking at its commutators. And of course, the most important commutator that comes to mind is the commutator of the Hamiltonian. There's a bit of calculation, of course, but it will not be a surprise that it does commute with the Hamiltonian. Its commutator is 0. It must be so because, as we remember, such a commutator, apart from I over h bar, defines us in quantum mechanics the derivative with respect to time of the operator in the Heisenberg picture. So if classically this was a constant of motion, it is quite conceivable that it is still a constant of motion in a quantum real, so to say. Now the next Hamiltonian is something that we know very well. Angular momentum is obeying the standard form. Something interesting is a commutator of angular momentum with components of the Runge-Lenz vector. It is very similar to LL. There are two ways of checking this last result. The first is just to use the definitions and do a tedious calculation. That's not what we will do. That's not advisable at all. Actually, the form of this commutator follows directly and only from the fact that A, this famous vector that we are dealing with, is a vector. Lemma for every vector, I will call it still A, Li with Aj is I H bar epsilon I Ijk Ak. I think it is good to know that this is the case. It can save you a lot of time and effort if you encounter this sort of commutation relation that you need. How to prove it? Here is how I prove it for you. You see, just like passing from Schrödinger picture to the Heisenberg picture is the same as passing from time-dependent states to the time-dependent operators, so is the case with all these transformations in space, either translations or rotations. In other words, we know very well that if we want to compute a state upon rotation with respect to the z-axis by phi, then we have to act with this unitary operator on the state. But if we think of a rotation of any vector A, yes, then we do not need to think about transforming this state, and performing this mean value calculation. We can again shift this fellow on this side, and we can say that this is e to minus I phi z divided by h bar a vector e to I phi. In other words, this can be called a transformed or rotated version of our vector A. Yes. Similarity to the translations in time is, I think, obvious. It is also having some kind of a very simple analogy with a so to say, school studies of transformations. Yes, so-called active and passive view. Either we can shift our sheet of paper, or we can shift in the opposite direction the axis of the reference frame. Yeah? Very similar. So, I want to apply now this notion that this right now AI e to I phi Lz h bar is a rotated A. And what is rotated A? Well, we know that how to rotate vectors, yes? I want to rotate around z-axis. So this is again my matrix cosine phi, sine phi, minus sine phi, cosine phi 0, 0, 1, 0, 0, acting on my vector A1, A2, A3. That's what rotation really means, yes, in the three-dimensional space. Now I have to raise complaint, so to say, to my boss, who asked me to use the blackboard and the chalk instead of these markers. Because with the chalk, I'm writing much bigger letters, and the blackboard is very small. So I have to erase and erase all the time. Sorry. Okay? So it's since I need everything which is on the blackboard. And yet I have to erase it. Okay, so look what happens. I could utilize this whole business with arbitrary phi, but it is sufficient to utilize this for infinitesimal, for tiny angles. Yes. So for tiny angles, I can write e to minus I delta phi Lz, or L3 maybe Lz, divided by h bar. I can approximate as 1 minus I over h bar times delta phi times Lz, yes? So the other guy, e to I delta phi Lz over h bar, likewise I can write as 1 plus I over h delta phi times Lz. Now, what you see is that if I restrict my attention now to the linear terms in delta phi, then what I will get out of this calculation will be AI, and that is from multiplication of this fellow times this fellow, and linear terms will have Lz once on this side, and from this fellow it will be on this side. Yes? So this is the same as writing plus I over h bar times delta phi and times the commutator of Lz and AI. If I'm not mistaken with the sign, I think I have done it right. Okay. If I do the same on the right side of this equation, then my rotation matrix changes into 1, 1, delta phi minus delta phi, 0, 0, 1, 0, 0. Right? And what I will get a vector of this sort. First will be 1 plus delta phi times A1. Second will be 1 minus delta phi, I'm sorry, A2. A1. And this should be A1, and this should be A2. And here I will get A3. Yeah? Now, if I now equate left and right side, of course these AIs will cancel against those, and I will get two commutators, Lz with L1, which will be I over h bar, of course, which will be proportional to A2, and Lz with A2 will be proportional to A1 with a different sign. I think by checking I's and h bars and so on and signs, you will find what I was promising. Now I want my commutators again. Of course, with Li it is also 0. Now Li with Aj, this is what I sketched. The proof is I h bar epsilon I jk times ak. Else are having also well-known commutators I h bar epsilon I jk times lk. And what remains, I don't know how to compute almost without calculation. Moreover, I have not done this calculation myself. I copied it from some notes. But in principle, of course, it's doable using standard basic commutators of x and p. The last and most complicated expression we get if we commute A's among themselves. And the result, you have to believe me, because I believe some textbook, is equal to minus I, A bar, epsilon I, J, K, times L, K, and unfortunately, twice Hamiltonian divided by M. Why unfortunately? Well, because the Lie algebras of Lie groups, something which is behind all our tricks with commutators helping to diagonalize various problems, should be defined by commutators of ordinate generators being combinations of generators themselves. And yet, we had an idea of adding one more constant of motion, vectorial constant of motion here, to our discussion, but unfortunately, the algebra is not closed because there is a product of angular momentum and Hamiltonian popping up. Yes? So what Fock, who was the first to use these tricks, what did he propose? He had an excellent idea. He said, let us not try to do our work in full generality, but let us look at the property of a bound states. Now, bound states are having negative energy, of course, yes, because, yeah, positive are scattering states, negative energy states are not. So if I imagine that I was able to diagonalize my Hamiltonian, then of course these negative energy states are forming some kind of a blocks. Within each block, the energy is the same of all the states, but of course there is some degeneracy. Of course, we all know what it is, but we will find out in 10 minutes. So I can restrict my attention, instead of, again, looking at it in full generality at all the Hilbert space of states of a hydrogen atom, I can restrict my attention to the subspace of a given energy. There is still multidimensional space, and I can think of working in this subspace. So in other words, assume that energy is fixed. So it's a number, or it's a unit operator within the subspace. Now, if so, then the trick is rather obvious. Yes, obvious for the very good guys. Let's define mu vector very much like Runge-Lenz, but not Runge, not Lenz, not both of them, not any of them, as the same old fellow multiplied by a square root of minus 2e divided by m. New object. Now, we have to obviously recheck, rewrite all our commutation relations. Just because A itself was commuting with a Hamiltonian, then of course our new vector A with a wiggle will not take us from a given energy to some other energy, otherwise it would not commute. So it is also nicely restricting to the given energy subspace. So is of course angular momentum. We know that angular momentum is conserved. So if I take some state, which is eigenstate of Hamiltonian, and apply angular momentum operator to it, or by the way, any rotation to it, then it must correspond to exactly the same energy, because these guys commute. Fine. So no problem with these two equations. Obviously no problem with this equation, of course. Look, no problem with this equation either, because I'm just introducing now the C number coefficient, and this fellow is linear in A and here linear in A. So in other words, we've got, with these new operators, we've got all familiar L's, okay. We've got this, remember, vector character was sufficient, yes? So, then this fellow. Okay. And this guy, if we substitute A and A with a wiggle, I have done something wrong. It should be M over to E, yes? No. It was okay. Sorry. Now if I do it, I know I had this way, and then of course it is minus 2E over M. So, if I substitute this fellow here, then I will get two such factors, and that will cancel with this, which is beautiful because it means that now I have algebra. These guys, they have exactly the same commutator as the angular momentum. I stress again that this commutation relations are written in the subspace of a given energy. And I will recover at the end what energy is if I diagonalize properly these commutation relations. There are two more equations, two more equalities that I want to keep on the blackboard. One is sort of obvious, namely that A scalar product is 0 or is 0. So of course is with the wiggle. This is kind of obvious. Classically they are orthogonal, and here also they are orthogonal. Less obvious, and actually again rather tedious, is another expression, namely if I take a square, that can be written as k square plus 2h divided by m times l square plus h bar square. This is less trivial, and again, I did not check it. Now, it's not the end of definitions. Let's introduce two new vectors, but this time it is lightweight exercise. This is simply Li plus Ai with a wiggle, and Si is a 1/2 times Li minus Ai with a wiggle. As you can guess, our next exercise is again to compute the commutators. That is now very easy. We have simple algebra on the left. We can use now this S and T, and that is okay. It's very easy. And the result, I will copy this. without organic. First, t squared is equal to s squared. These are not completely independent vectors. Oh, it's very easy to check. If I square it, then I have this square plus the scalar product, yes? And the scalar product is 0. So regardless whether it's plus or minus, I'll get the same quantity. So this is obvious. Now, it is also very simple to check that these guys are completely independent. So they commute. And that now both Ti, Tj, as well as Si, Sj is simply h bar epsilon ij k, tk, and this is I h bar epsilon ij k, sk. So what do we have? We are working, as I was promising, we are working in the subspace of a given energy. So this energy eigenvalue is somewhere swallowed in the relation between A and a wiggle. But the resulting set of commutation rules are very intriguing, because what do we have now? We have two operators, one vector operators, one S, the other T, both satisfying the set of commutation relations of the standard angular momentum. Instead of standard single L, yes, we have like two of these guys, except that their squares are equal. Moreover, they mutually commute. So, invoking our knowledge of the properties of the angular momentum, which were derived and re-derived many times, we can look at s squared acting on a state in the form h bar squared times t plus 1 times this state, where t, like in any angular momentum problem, will be 0, a half, 1, 3/2, and so on. Yes? Because S vector is angular momentum vector from the point of view of commutators, and we derive this property of L squared only using the commutation relations. So one eigenvalue that I will put here is just t, and it doesn't matter whether I act on this fellow with s squared or with t squared. But these fellows are angular momentum-like, so together with this s squared equal t squared, I can diagonalize simultaneously one of the components of S and one of the components of T. So I have room for two magnetic quantum numbers. So I can put MS and MT, MS and MT as the additional quantum numbers that are really spanning for me this subspace of given energy. We know, knowing square of the angular momentum, we know what is the number of MS's that are allowed. This is equal to 2t plus 1, like 2l plus 1 was 2 weeks ago, yes, probably some years ago for all of you. We know also how many values we can have for MT. Well, identical, also 2t plus 1. So in other words, full degeneracy of this manifold that I'm spanning now with, say, S raising S lowering, T raising, T lowering, full number of vectors is 2L plus 1 squared. You see something correct is already popping up. Because ST changes from 0 to 1/2 to so on. These are just squares of consecutive numbers. 1 square, 2 square, 3 square, and so on. You know very well that this is really precisely the degeneracy of the hydrogen atom. So by playing this game, we found a degree of degeneracy of in every negative energy eigenvalue subspace. You could still ask, hey, and are we getting correct energy levels? Are the values of E correct? Indeed they are, and for that, one has to use these formulas again. We know how A, through this formula, is related to E. We know how A tilde is related to S and T, and by plugging this thing here, one can compute the energy which is given here in this coefficient. It's just algebraic expression. I have done it myself, believe me. And the result is, as books are telling. So for given T, it is minus M K squared divided by 2H bar squared times squared. That's it. So what I'm saying is that without ever invoking any differential equation, one can find the eigenvalues of the hydrogen type Hamiltonian eigenvalues, negative energy states. It's restricted to the negative energy states. Plus we can find the degeneracy. Of course, it's additional and interesting question of how these wave functions look like. And for that, we have to look at the differential equations. But other properties, also many properties concerning various integrals, various scalar products and so on, they can be also, just like for the angular momentum, they can, or just like for the harmonic oscillator, they can be very often worked out using the algebraic properties. Yes. What immediately comes to mind is that there is this maximal state when, you know, Ms and Mt is equal to minus T, and on that you can build the hierarchy of other states by applying S plus and T plus operators, and this way, from solution of one problem, you can generate all the other states. A lot simpler than, a bit simpler than by solving the differential equations. As I was mentioning in our discussions, I don't think there is even a single truly relevant other problem that is solvable by this algebraic method. There are, of course, many that mathematicians know of, and they would be rather defined by the symmetry group than by the specific Hamiltonian. So they typically lead to something which is not of great interest or importance for physics. Okay, so this way I finished my little excursion into algebraic methods of solving quantum mechanical problems. And I now want to go to something that in my original lecture notes was sketched a bit earlier, namely to philosophy, that's a big word, to interpretations. Interpretations of quantum mechanics. tell you from the very beginning that there are several competing, that those who like one usually do not like the others, and saying like, using the term like, is quite appropriate because there is no way that you can prove that one of them is superior. So it's a matter of taste. It's very much a matter of taste. Certainly the most widespread is typically called Copenhagen representation. Interpretation. And usually people associate two names with this interpretation. That of Heisenberg and that of Niels Bohr. If you scan literature, then you can find out that at times they agreed, at times they did disagree. So probably it's impossible to find a set of statements that are really canonical statements in this representation, in this interpretation. And yet, I think it is most widespread, not the only one by any means. So let me just say a few words, maybe 10 minutes or so, about it. Well, there are two important aspects of any interpretation. One is meaning of the wave function, and the other is understanding of the measurement. The quantum measurement problem. Let me start with the second, which in this interpretation is the weakest, typically the weakest point. For this point, many criticize original Copenhagen representation. So in this very orthodox interpretation, measurement is a truly mysterious effect of flirt between classical measurement apparatus and the quantum system. And it's typically assumed, of course, as I was telling you from the very beginning, that if we are trying to measure quantity A, then the only possible outcomes are the eigenvalues of these guys. And after the measurement, the system remains in this particular state that it happened to be measured. So there is so-called sudden collapse of the wave function. It's very hard to understand what does it mean. And until we try to figure out what is the meaning of the wave function itself. And here is something which is a very strong aspect of Copenhagen interpretation. For Copenhagen interpretation, the wave function is the state of the information we have about the system. It's not like classical electric field, which is telling you what is the value of electric field amplitude in every point of space and maybe time, if the evolution is invoked. It's an important notion of information being hidden in the wave function. And I think there are many processes and many experiments which are very hard to understand if one attributes some kind of the element of reality to the wave function and not treat the wave function as the set of informations that we have. And I will give you one example, kind of thought experiment, which I think is telling. Imagine that we've got a cavity where there are photons of some particular mode. And imagine that someone prepared a very particular state state of the vacuum plus 10 photon state. Now, proper definition of the superposition of states with different number of photons. I chose extreme that one element of the superposition is just vacuum, 0 photons. So, if I would define, as will happen maybe next week or maybe in 2 weeks, operator of defining the number of photons, then it is what? It is proper 1 over square root 2. Yes. It will be 1/2 probability that it is 0, plus 1/2 probability that it is 10. So mean value will be 5. Yes. So mean photon number is equal to 5. I think you agree. It's either 0 or 10, so the mean value is 5. Now imagine that we've got detectors all around, and as every cavity, our cavity is also leaking photons outside. Yes, there's always some probability that photon will escape. And imagine that we've got a click here. So one of these detectors detected photon coming from this cavity. What do you think we have inside? What we have inside must be 9 photon state. Yeah? We extracted 1 photon. It cannot be out of vacuum. It can only be from this other component. So now, after this measurement, the number of photons inside is 9. Mean number is 9. However, no energy floated in. How come? Are we violating conservation of energy or something? Of course not. If we treat information about the state as information and not actually real 0 and 10, then it's okay. We learned that something leaked out, so we infer from this that there must have been photons there, and the only number of photons that was there would be 10, so the remaining is 9. Energy is conserved, everything is fine. I think for me, this is an example of the most decisive argument in favor of looking at this sort of expressions and invoking in my imagination that this is the information about the state of the field, of this photon field in the cavity, and not some real field, yes, not some real field. On the other hand, I stress that it shows adequacy, or at least the nice aspect of treating the state, superposition state, as information about the system, and rather than the system itself, an element of reality, as these philosophers like to call it. But this probabilistic interpretation, either this or that, from my example, is not really basically quantum. And I like the anecdote that I will tell you now. Imagine there was a boy. Once upon a time there was a boy who was getting some kind of a weekly allowance from his parents every Saturday. And this boy liked ice cream. And the ice cream, a cup of ice cream, a scoop of ice cream, costs 1 zloty. This fellow likes this ice cream very much, so he typically goes each day going to school, going back from school, is thinking he's buying ice cream. So, typically, when when Saturday comes, before he gets this 10 zloty from his parents, he has 0 zlotys. Now imagine, so when we see this boy walking on the street on Saturday, we are not sure. It's either in his pocket there is 0 zloty or 10 zloty. However, imagine that we see this fellow with an ice cream in his hand. We know that 9 zloty is in his pocket. Yeah? It's very much like here. And absolutely no quantum mechanics behind. But, obviously in my little anecdote, I was talking about information. Yes? So this is really what is deeply in the Copenhagen interpretation. Now, I mentioned that even though typically when you look into the books, people attribute this interpretation to Heisenberg and to Bohr, but they also disagreed a little bit. And what was it's very hard for me to understand what they disagree upon. The best I can explain is that once you talk about information related to the state, then you probably tend to you do or you don't do, you tend to think about the subjective aspect of the problem. That if the information is the basic ingredient of quantum theory, then perhaps given the same leaky cavity and initial state prepared, this fellow and me, we might have different set of informations about it. And maybe we should interpret this differently. That for us, for me, something else should be inside, and for him something else would be inside. Even if we do diagnosis of many various measurements. I am not subscribing to this. I think there is an element of objectivity to this set of information that defines the state for us. This question of how objective information about the quantum system is still being pursued. And there are papers written about it. And in particular, this question of objectivity was raised, I don't know, 8 or 9 years ago, 8 years ago, I think, by our colleague from Los Alamos, Wojtek Żurek, who is a really excellent physicist and whose name appears very often in various lectures, in various contexts. He was trying to think or to describe this notion of objectivity, how to define it properly, that for him and for me and for you, the given state is identical. Something that we are sure at the classical level, yes, we look at this remote control thing, and we believe that we all see the same remote control thing. So, here we are really touching, well, close to philosophy. It stops to be a philosophy when people are trying to do something in some sense reasonably by looking at the given models and trying to build something from scratch, so to say. Another completely different line of thought is to demystify this notion of instantaneous collapse of a wave function at the measurement. To demystify this, some people, many people, looked at various specific quantum physics models of the open system. Small quantum system interacting with large quantum system, and interpreting the question, the problem of measurement in terms of a realistic interaction between the small and big. Yes. And there are, of course, interesting, important papers written on that. They go under the name of the coherence interpretation of the measurement. Okay, I zoom through the several conflicting, in some sense, interpretations, and in a few words, I will tell you what another interpretation is, which is due to a fellow whose name is Everett. It's called there are some people that like it, which implies that I don't like it. But I will tell you nevertheless. You know, all this sudden collapse of the wave function can be viewed in the following way. Suppose we've got 0 plus 1, yes, some value of, I don't know, momentum, or angular momentum, or here, of this, and we measure this angular momentum of this particular operator, and we've got value 1. What this interpretation says is that at the moment of measurement, there was a bifurcation of the whole universe. And there is another different universe in which the same measurement gave 0. So in other words, there are as many bifurcations as there are measurements of something which has quantum ambiguity, that could be this or that or that or that. Yes? If there are 55 different eigenvalues present in a given state, then there are 55 universes appearing, and if we find that out of this 55, what we measure is 13, it only means that we happen to be in this universe where it was 13. I'm laughing because I really can't stop wondering how come some people like it. In philosophy, there is a well-known principle of Occam razor. It's a statement which says, do not introduce unnecessary notions. Stay with a minimal number, so to say, of notions. And my goodness, this avalanche of universes which are being formed at every measurement worries me, because I have never seen any other universe, and they seem to be completely unnecessary. Everett himself was a student, graduate student of John Archibald Wheeler, very famous physicist. And this interpretation, even though it was a bit unclear, people say, in his PhD, was somehow developed in his doctoral thesis and did not catch much attention of the physics community. So this fellow, Everett, became disillusioned with science and became kind of entrepreneur and technician and spent most of his life earning money and developing useful things. I don't know what did he develop, but probably they were more useful than his interpretation. Bryce DeWitt, very famous American physicist, maybe 10 or so years later, he has done it in the 50s, but Bryce DeWitt somehow became fascinated by Everett's idea, and it is DeWitt who really made it popular. So I don't want to spend more time on it. I think every decent physicist should know that such a strange thing does exist. Okay. Now, my last point for today is much more serious, even though I also don't like it. It's an observation or interpretation introduced by Dave Vaughan, another American physicist. Interesting enough, I will tell you what his interpretation is. Interesting enough, he introduced some interpretation, believed that this is a really great discovery, and then wrote also a textbook on quantum mechanics, which was probably based on lectures he had to give to students. And this textbook is pretty orthodox. I doubt whether he even mentioned his interpretation in the book. The book is not touching this touchy thing of interpretation. I mean, there is a whole school of thought of not thinking about it at all, and maybe about this interpretation, and maybe, I don't know, the problems will disappear or something. There is an American physicist, Mermin, who wrote a lot about this foundation, physicists, yes. Shut up and calculate. So that's what most teachers are, basically. Even if they don't say this, they try to sweep these questions under the rug and without expressing it so clearly, they say, shut up and calculate. Okay, so what is the Bohmian interpretation? Let's start with the good old friend, namely Schrödinger equation. And then we've got minus a plus squared Laplacian over 2m plus some potential, and this multiplied by psi of x. Now, 3D of r, 3D. Almost immediately, about a year after Schrödinger wrote his Schrödinger equation, German physicist Madelung had an idea of rewriting this equation, which of course is for complex psi, in the form of set of two equations for real variables. However, he did not choose a real part of psi and imaginary part of psi, but rather the modulus and the phase. So in other words, Madelung wrote wave function in the form of a square root of a density, yes, of the probability distribution, times e to I phi. You can do it, and what he did, he substituted this into this equation and derived the equation for rho and the equation for phi. First order differential equation for rho and for phi. Now let me tell you that the easiest thing to do, if you want to do this exercise, is to substitute this, do these differentiations, and then multiply everything by e to minus I phi, or in other words, take in every term e to I phi outside and then cancel it. That's the way. And then identify real part with real part, imaginary part with imaginary part. It's a bit tedious, but well, it's a little exercise. Now, the resulting equations are kind of familiar. So the first of them, which is telling you what is derivative of the law or probability distribution, is this plus divergence of rho times h bar over m times gradient of phi equals 0. Now, this should remind you, of course, a continuity equation for any flow or for any flow. Yeah. However, for this to turn into continuity equation, we have to interpret the gradient of the phase as a velocity. So it makes sense to write V as h bar over m times gradient of phi. There is nothing more right now than the abbreviation, yes, for the gradient of phi. Now with this substitution, this becomes a very conventional thing, rho dot plus divergence of rho v equals 0. Of course, we all remember, I don't know, even if you never had a lecture on hydrodynamics, you had a lecture on electromagnetism, and if this would be the continuity equation for the charge density, then this equation you know very well, expressed in terms of integral form, is the conservation of charges. So here is a conservation of probability. If I would take some finite, well-defined volume in space and integrate the rho over this volume to get how much of this fluid, let me call it, is inside, then I would say that it changes only because of the flow from the borders, yes? You are all familiar with what I'm saying, yes? Right? The Stokes theorem. Now, question is, what is the equation for phi dot? An equation for phi dot is not really very telling, but if we take gradient of two sides of this equation, so we will introduce again this velocity, then this equation is kind of nice. It looks like this. M derivative of v, so acceleration, equals minus gradient times mv squared over 2. Everyone knows that that's, of course, kinetic energy. Plus this potential and one more term. And this one more term is kind of ugly, causing a lot of problems if one tries to do anything numerically. It has h bar, then it has Laplacian over square root of rho divided by square root of rho, and that's it. Well, Madelung thought that these are very neat equations because they are like hydrodynamic equations. This is like Newton's law, and this is, of course, conservation of probability. And this would be like a potential, and gradient of this minus gradient of this would be like a force. This is fine, this is fine, and then Madelung said, aha, this last term is really the trace of quantum mechanics. That's how quantum mechanics differs from classical hydrodynamics of non-interacting ideal fluid. Also incompressible. Madelung hydrodynamic equations never replaced the Schrödinger equation, and they are not even very often invoked in the standard courses of quantum mechanics. Why? Because even though this classical interpretation, they are very much like a flow of classical particles except for some crazy quantum pressure term, even though they are very close to the classical mechanics, they are lacking this beautiful property of linearity of Schrödinger equation. The fact that, if you have two solutions, then combination of these two solutions is again a solution. This, rewritten for rho 1, rho 2, v1, v2 is crazy. It's a complicated expression that nobody would like to deal with. Of course, this linearity, the fact that superpositions are solutions, is still hidden here, but hidden very deeply. Nobody wants to touch it from this point of view. Nobody except Dave Bohm. Dave Bohm came to this equation and he said, okay, if not for this stupid quantum term, this would be like a dust of particles that are floating in space, just classical particles that are having classical trajectories. So Bohm had an idea that classical trajectories do exist also in quantum physics. That particles travel along well-defined path, except that this well-defined path is a solution of equations of motion. Yeah, it's like Euler equations in hydrodynamics, but with some crazy additional quantum force. He coined, I think, the term quantum pressure term. So in other words, in this Bohmian interpretation, I'm always confusing these two words, if I have a double-slit experiment, and I'm sending electron by one after another, then according to each electron in a given particular realization goes through only one opening, one slit. But the way it behaves between the source and the screen outside depends on this solution of a quantum problem. Namely, it depends. This is like a pilot wave, as these guys are calling it, that is telling you how to behave. And he, of course, not he, I don't know, but some followers, and some of these followers I even have lectures of, they computed a lot of these trajectories for various quantum mechanical systems. And these trajectories are incredibly complicated and are crazy. They are not, even though the potential they are traveling in is very smooth. And the classical trajectory would be very smooth. Quantum trajectory, or the trajectory of quantum particle in the Bohmian representation, would go like crazy. And just because of this craziness, the presence of the other slot, which is open, is changing completely properties of the trajectories that are going through this other slot. In other words, there is some action at a distance, so to say, which is hidden in the properties of the wave function solution. But the wave function in this interpretation, has very little to do with the trajectory of single particle. A single particle, okay. First you have to solve the Schrödinger equation, then you have to compute this quantum pressure term, and then you have to solve the Newton equation with its funny force, and then you will get the trajectory. That's what these guys say. Again, usually the objection raised against this interpretation is that it again multiplies, so to say, the notions, because there is separately all the machinery of solving Schrödinger equation, and a posteriori, only afterwards, you can also look at the way given particle behaves if solution of the kind computed before, computed earlier, is realized. So I think it's very interesting. It's not so complicated, strange to me like Everett's, but it's very interesting interpretation, which I think is also suffering this Occam-Razor criterion. Namely, it doubles again the notion of this wave function, which is in this case called the pilot wave, and there are particle trajectories which are still completely, how should I say, causal, yes. But this causality is there provided we understand that this particle travels in the external field, which is very complex. Okay. Now next week I'm going to talk about, in the first part of the lecture, I'm going to talk about Feynman interpretation of quantum mechanics, which takes absolutely contrasting opposite view than Bohmian.